In the previous video, we tried to understand construction part of differential amplifier. We said the circuit should be symmetrical, and differential amplifier is nothing but a direct coupled amplifier where the emitter of the two transistors are directly connected to each other. And when we say the circuit should be symmetrical, that means RC1 should be equal to RC2, Q1 should be equal to Q2, R1 equals to R2, and RB1 equals to RB2. I will tell you why this is necessary. And of course, as minus VCC acts as a constant current source, IE1, that is emitter current of Q1 and emitter current of Q2, the addition of these two will be constant. Okay, now let us try to understand the working of a differential amplifier. Of course, as I said, it will have two inputs. So first what we will do is we will apply voltage at V1 so that V2 उस time पे ground पे connect होना चाहिए, and if you apply at V2 then we have to connect V1 as ground, and we have to see what type of output we get at VA and VB. So advantage of differential amplifier is instead of one input one output, you have now two inputs and two outputs. So that is one more advantage of a differential amplifier. Let's say the input is applied. This is the positive half cycle, this is the negative half cycle, this is at V1. Okay, V1, that means voltage applied across here, plus minus. Now as a sinusoidal waveform is applied and input signal is applied to V1, of course it will affect the biasing of transistor Q1 here. Now what happens is during the positive half cycle, the forward bias of PN junction of this base emitter junction of transistor Q1 will increase. During the negative half cycle, the forward bias of this base emitter junction of Q1 decreases. Let us try to understand through a transistor operation. Okay, so this is your say NPN transistor, this is emitter, this is base, this is collector. Emitter base junction should always be forward bias. So for forward bias, the polarity should be like this: negative, positive, negative, positive. Okay, and PN junction, the base collector junction should always be reverse bias. So the polarity should be like this. This is called as VCB, this is called as VEB, that means the forward bias. This is the forward bias voltage, this is the reverse bias voltage. Okay, now this negative terminal will repel the electrons, right? Electrons which will move from N region into P region, which will constitute emitter current IE. Now out of that large amount of electrons which is moving from emitter to base, few electrons will recombine with the holes in P region, which will constitute the base current IB. Remaining all the electrons will enter into collector and get attracted by the positive terminal of the VCB, that will constitute collector current IC. So out of 100%, only 2% goes into base and 98% goes into collector. This we have repeatedly understood. Okay, so we say IE is equal to IC. Now what happens if forward bias voltage is increased? I have explained you this thing when we try to understand transistorized voltage regulator in chapter 2. So what happens if forward bias voltage increase? If forward bias voltage increases, more charge carrier will move out of emitter into base, that means emitter current will increase, and as IE is equal to IC, IC will increase. And if forward bias voltage decreases, what happens is less amount of charge carrier will move out of emitter into base, so IE will decrease, and as IE is equal to IC, IC will also decrease. So this has to be remembered so that we can understand the working of differential amplifier when input voltage is applied at V1 for positive as well as negative half cycle. So what I said, during the positive half cycle, when V1 is applied during the positive half cycle, the forward bias of Q1, the forward bias, that means base emitter junction is more forward biased, and if it is more forward biased, forward current IE1 increases. So I draw a graphical representation that IE1 increases. As IE1 or I is equal to IC, so IE1 will be equals to IC1, IC1 will also increase. And if IC1 increases, you see what is the equation for VA? VCC minus IC1 into RC1. VCC and RC1 is constant. If IC1 increases, VA decreases, right? VA will decrease. Okay. Similarly, during the negative half cycle, IE1 decreases, therefore IC1 decreases, and if IC1 decreases, VA will increase. Okay, so VA will increase. So now what you can see in the diagram is when input voltage is applied at V1, what you get at VA? You get 180 degree phase shift between input and output. The phase we understood this phase difference or phase angles difference between the two signals in chapter number 1, application of CRO, cathode ray oscilloscope. In that, the fourth application, that is phase difference between the two input signals, that is where we have understood this is these two signals are 180 degree phase shift. Now the working is not done. As IE1 increases, we have mentioned that IE1 plus IE2 should remain constant. So if IE1 increases, to keep the output constant, to keep this value constant, if IE1 increases, IE2 will decrease, because I have told you earlier, any change in Q1 will produce change in Q2 because Q1 and Q2 are directly connected. Okay, so any change in IE1 will produce corresponding change in IE2. That means when IE1 increases, to keep the output constant or to keep the current through the circuit constant, IE2 will decrease. As IE2 is equal to IC2, IC2 will also decrease, and if in this equation IC2 decreases, VB increases, so VB will increase. Okay, similarly during the negative half cycle, as IE1 decreases, IE2 increases, IC2 decreases, IC1 decreases, therefore IC2 increases, and when IC2 increases, VB decreases. Okay, VB decreases. So now for one input which has been applied at V1, we get two outputs, one at VA and one at VB. Okay, one at VA and one at VB, but at VA you are getting 180 degree phase shift, and at V1 you are getting 0 degree phase shift. And if the current which is flowing through both this circuit will be common, or the voltage drop which is produced will be same. So what happens is these two signals are 180 degree out of phase, they will cancel each other and the output will be 0. That means in the absence of input signal, the output at this point should be 0. But as soon as input is applied, we will get two outputs, one 180 degree phase shift, and at VB you will get 0 degree phase shift. So the same thing we can understand by, say we apply voltage at V2. So when you apply voltage at V2, the first thing which will get affect is the base emitter junction of Q2. That means IE2 will change, IC2 as IE2 changes, IE1 will change, IE1 will change, IC1 will change, and when IC1 and IC2 will change, VA and VB will change. So that is what we have to understand. So when input is applied at V2, what you can see is IE2 during positive half cycle, IE2 increases, therefore IC2 will increase. During the negative half cycle, IE2 will decrease, IC2 will decrease. And if IC2 decreases, VB, what happens to VB? VB will increase. Okay, VB will increase. Okay, during the negative cycle, IC2 increases. So if IC2 increases, VB decreases, and during negative half cycle, VB increases. Similarly, as IE2 will change, IE1 will also change. During the positive half cycle, as IE2 increases, IE1 decreases. This is the waveform for IE2. and then IC1 will be exactly similar to what? IE1. And if IC1 decreases during the positive half cycle, IC1 decrease, VA will increase. If IC1 increase, VA will decrease. So the waveform at VA will be like this. So what you can see is that when V2 input is applied to V2 and V1 is grounded, input is applied to V2 and V1 is grounded, what you get is you get two outputs, but now at VB you get 180-degree phase shift, and VA you get 0-degree phase shift. Okay, so this is what is the working part of your differential amplifier. Now by all this study, we can conclude and we can design the symbolic representation of differential amplifier. Now differential amplifier has 2 inputs, 2 outputs and 2 power supply. The power supply is plus VCC, this is minus VCC, this is V1 and this is V2, this is VA and this is VB. What I will do is I will give sign convention so that we can understand the operation of the differential amplifier right by the symbolic representation. Suppose if I mention that V1 to be as, I will denote it by a negative sign. Okay, now what you can see is when input is applied to V1, what you get at the output at VA, 180-degree phase shift. That means when you give positive you get negative, when you give negative you get positive. So output will be exactly 180 degrees. So if you give negative at V1, you get positive at VA. At the same time, when the input is given to V1, when you give positive, you get positive at output. When you give negative, you get negative at the output of VB. That means V1 and VB are in same phase. So I will represent VB as negative. Okay, similarly when V2 is applied, now V2 we will mention it as positive. So when input is applied to V2, what you get at VB? 180-degree phase shift, opposite polarity will get. So when positive is given, you will get negative at VB, and when positive is given to V2, what you can see is you are getting 0-degree phase shift. So whatever be the polarity here, the same polarity will be here at VA. So this is the symbolic representation of differential amplifier. So we have understood construction, advantages and working of differential amplifier. Now we will use this differential amplifier to design operational amplifier. I hope you have understood. Now next we will try to understand the block diagram of operational amplifier. In the first video itself I have told you that to design operational amplifier, the basic building block is differential amplifier. So we have to use differential amplifier. So in the last video we tried to understand the working of differential amplifier, where you have 2 inputs and 2 outputs. Okay, so when input is applied at V1, you get 180-degree phase shift at VA and 0-degree phase shift at VB. And similarly when you apply input at V2, you get 0-degree phase shift at VA and 180-degree phase shift at VB. So that was the operation. And one more thing which we have understood in differential amplifier, that it amplifies the difference between the 2 input signal. That means it will always reject the common signal, and mostly the common signal will arise from the noise. So basically it will remove the noise or the disturbance which was caused by the ambience or ambient environment to the negligible value, to 0. So that is the advantage of differential amplifier, and the ability of the differential amplifier to reject common signal and amplify only the difference between the 2 input signals is called as CMRR, common mode rejection ratio. Of course it will be a ratio of gain when the inputs are different upon gain when the inputs are common, and of course when the inputs are common, the gain should be 0, and if it is 0, anything divided by 0 is infinity. That means CMRR should be very high for a differential amplifier, of course. And as they are They are example of direct coupled amplifier. Differential amplifier is the example of direct coupled amplifier. The voltage gain will also be very high. So for operational amplifier, the first block is a differential amplifier. We call it as differential amplifier 1 with two inputs V1 and V2 and two outputs VA and VB. Okay, so and there is one more block called as constant current source. Okay, so this constant current source is nothing but the second power supply, right, minus VCC, which provides constant current for the two emitters of the transistor. So make sure that the operating point of the transistors remains stable, that is between that of saturation and cutoff. So we have a differential amplifier with a constant current source. This is the first stage of operational amplifier. That means operational amplifier will always have two inputs. Okay, now the advantage of using a differential amplifier, that CMRR, you get very high CMRR value and high voltage gain. We will call it as AV, voltage gain. As I've already told you, amplifier is a circuit which amplifies the strength of the input signal at the output. So if it is 2 and input voltage is 2, output voltage is 10, it will be output upon input, which is 5. Though this is the gain factor. So gain factor of differential amplifier is very high. But for designing operational amplifier, the gain should be very large. We need to have an amplifier which amplifies small signals into a very significant value at the output. So what we do is, the second stage of, or the block diagram of operational amplifier is also a differential amplifier. Okay, differential amplifier, I'll call it as differential amplifier 2, but the output is single ended. That means one output will be grounded and only one output will be continued. Now the advantage of using second differential amplifier is, again, CMRR is infinite and the voltage gain becomes infinite. Using two stage of differential amplifier will increase the voltage gain to almost infinite. That means whatever be the input voltage, the output voltage will be very, very large. Okay, and of course CMRR will be infinite, which is the most important factor of a amplifier circuit. Okay. Now the third stage is called as buffer stage, or it is common collector configuration of transistor. Common collector configuration means where collector is common for both input and output. And when we try to understand the transistor's basic concept, we said that for the common collector configuration, voltage gain is unity. That means it is not used for voltage gain, it is used for current gain. Okay, only used for current gain. So here also it is the basic purpose of this common collector configuration is of course two things: to increase the current factor and it acts as a buffer stage between the second and the fourth stage. I will tell you what exactly it means by buffer stage. Okay, so here the current factor will increase. Okay, voltage gain is already infinite. If you increase the current, power will increase, so power factor will increase in the third stage. This circuit is also called as common collector configuration or emitter follower. Okay, now for this buffer stage or the common emitter configuration, input impedance is very high and output impedance is low. This is high and this is low. Okay, now when I say input impedance, it is the overall resistance at the input stage, and when I say output impedance, it is the overall resistance at the output stage. This is the characteristics of common collector configuration. So at the output stage, what happens is the output stage is voltage level shifter. Okay, voltage level shifter. That means in the absence of input signal, the output must be 0. If the output is not 0, the output has to brought back to its 0 level. Okay, and that process is called as offset null. Please listen to it carefully. What I said, in the absence of input signal, the output must be 0, but there are probability that the output may not be 0. Of course, that if that is not 0, that means that value is unacceptable. There should not be any output voltage, so the output voltage has to be brought back to 0 level, and that is done by voltage level shifter, and the process of making the output to 0 is called as offset null. So basically the buffer stage or the common collector configuration or the emitter follower, what it does is it matches impedance between the second stage and the fourth stage, which is the voltage level shifter, because the common collector configuration has high input impedance and low output impedance, so it will be used for impedance matching. Okay, and here we will take this is what we have done. We have continued with VA and VB has been grounded, so continued with VA. Let's say here we get the output voltage. So now when you draw the symbolic representation of operational amplifier, we will use the symbolic representation of differential amplifier to represent operational amplifier, but here it will have 2 input and only 1 output and 2 power supply, plus VCC and minus VCC. Now what we have done is the 2 inputs will be V1 and V2, and the output we have continued with VA and we have called it as V0. So when input is, suppose this is the terminal, say negative terminal, we call it as inverting terminal. V1 represented by minus sign is called as inverting terminal, because we know when input is applied at V1, what you are going to get at VA will be like this. That means the output will be inverted. There will be a phase shift of 180 degree between input and output. That is what we have understood by the working of differential amplifier. So what you're going to get at input, so this is when the input is applied at V1 like this, what you're going to get at the output is an amplified output, but it will be inverted. Therefore this terminal is called as inverting terminal, right? Similarly V2, when input is applied to V2, what happens is, when input is applied to V2, VB will be 180 degree out of phase, VA will be same phase. As we have grounded VB, we have continued with VA, what you are going to get at the output will be like this. That means you get zero phase difference between input and output. So this V2 is called as non-inverting terminal. Okay, non-inverting terminal, inverting terminal, non-inverting terminal. So this is a symbolic representation of operational amplifier. So that is how you have to remember. If there is a minus sign to a terminal, that terminal will be inverted, because when input is applied to that terminal, the output will be 180 degree out of phase. And when input is applied to the plus terminal, which is called as non-inverting terminal, there will not be any phase shift. You give positive, you get positive, you give negative, you get negative. So there will be a 0 degree phase shift. So this is the symbolic representation of operational amplifier. Okay, now the characteristics. This question has been asked several times in your board exam. Characteristics of operational amplifier. The first characteristics, what we can see from the block diagram itself, that CMRR is infinite. Second, voltage gain AV is infinite. This is open loop gain. I will explain you what exactly it means, what exactly we mean by open loop gain in the next video on the next concept. Okay, so these two are very evident, we have already understood. Now differential operational amplifier is designed using differential amplifier, and differential amplifier is nothing but a direct coupled amplifier. And in a direct coupled amplifier, if you draw a graph between gain and frequency, yes, we have understood gain and frequency. The gain is constant, that means bandwidth is infinite. Okay, so the next is bandwidth is infinite. Fourth, as we have connected common collector configuration and differential amplifier, all this circuit has high input impedance and low output impedance. So input impedance is infinite. Fifth, output impedance is 0. I'm considering ideal characteristics of op-amp, practically no practically. Okay, it is ideal characteristics, that's why I'm giving specific value. Of course input impedance is infinite, of course it cannot be infinite, it will have a certain value but it will be very, very high. Similarly output impedance, it will not be 0, it will have some value but it will be very, very small. And 6 is slew rate is 0. Slew rate is the time taken by the output to reach to its final value as soon as input is changed. इनपुट चेंज करने के बाद में आउटपुट को अपने फाइनल वैल्यू तक पहुंचने के लिए जो टाइम लगेगा, वी कॉल दैट एज स्लीव रेट. Same thing we have understood in chapter number 3, logic families. The definition was propagation delay time taken by the output to reach to its final value as soon as input is changed. That value there in digital, it was called as propagation delay time. Here it is called as slew rate. Slew rate is 0. That means when the input is changed, immediately the output changes. Okay, so that should be the property, or that should be the ideal characteristics of your operational amplifier or of any amplifier you design. So these are the basic 6 ideal characteristics of operational amplifier, which is of very, very important. Okay, I hope you have understood.